All right, welcome. Today, we're going to get into something really cool, the dynamic behavior of a fundamental circuit in power electronics. We're going to see how a simple little team of three components can actually have three very different personalities.
So, here's our game plan. First, we'll get introduced to the circuit itself. Then, we'll dig into the rules that make it tick. After that, we'll explore its three unique personalities, walk through a real-world example, and then, this is the important part, we'll see why any of this actually matters in modern electronics.
Okay, let's just dive right in. First things first, we need to meet the components of our circuit. It looks simple, but trust me, its behavior is surprisingly complex and interesting.
And here it is. We've got our three key players on the team. The resistor, which is kind of like the brakes on the system. The inductor, which stores energy in a magnetic field. And the capacitor, which stores it in an electric field. The real magic happens when they all start working together, the very instant we close that switch.
You know, every system in the universe follows a set of rules. And for this RLC circuit, those rules just happen to be written in the language of math. So let's take a look.
Now, don't let this equation scare you off. Seriously, all it is the official rule book for our circuit. It's the blueprint that tells us exactly how the current is going to behave over time. If we can solve this, we can predict everything about the circuit's personality.
To really crack this equation, we need to understand two key ideas. The first one is called the damping factor, or alpha. The easiest way to think about it is as the circuit's braking system. The resistance R is what puts the brakes on, and this alpha factor tells us just how hard it's braking.
And the second idea is the natural resonant frequency, omega naught. This is the circuit's natural tendency to wobble or ring, all based on its inductor and capacitor. It's the frequency it just wants to vibrate at if you let it.
Okay, now this is where it gets really interesting. What happens when we compare these two values? When we pit the brakes against the wobble? Well, that relationship gives our circuit one of three totally distinct personalities.
So this is the big question, right? It's basically a tug-of-war going on inside the circuit. On one side, you have its natural desire to oscillate, to wobble back and forth. And on the other, you have its tendency to slam on the brakes and dissipate all that energy. Whoever wins this tug-of-war defines how the circuit acts.
To really get this, just think about the suspension in a car. If it's overdamped, hitting a pothole feels really stiff and slow to recover. But if it's underdamped, the car gets super bouncy and just keeps oscillating up and down. It's the exact same principle we're talking about here. First up, we've got the overdamped case. This is where the brakes, our resistance, are just slammed on hard. The damping is so strong it completely chokes off any desire the circuit has to oscillate. The current just kind of smoothly and maybe a little sluggishly rises up and then fades away. No drama. Then you've got the critically damped case. This is where alpha and omega naught are perfectly balanced. This is the sweet spot. It's the absolute fastest way to get the response you want without any of that overshoot or ringing. It's the gold standard. And finally, there's the underdamped case. Here, the natural frequency, the wobble, wins the tug-of-war. The brakes just aren't strong enough to stop it. So the current overshoots, swings back and forth, and creates this really cool decaying wave. Okay, theory is awesome, but let's see how this stuff actually plays out. We're going to jump into a specific case study right from the source text and plug in some real numbers to see what an underdamped circuit actually looks like. So here are the exact values for our example. We've got a 220-volt source, and the specific R, L, and C values you see here. Now, let's figure out what kind of personality this particular circuit is going to have. Okay, so we run the numbers. Our damping factor, alpha, the brakes, comes in at 40,000. But the natural frequency, the wobble, is way stronger at 100,000. And right there, that confirms it. Our circuit is underdamped. The wobble wins. And that math leads us to this final equation, which perfectly describes the oscillating, decaying current we're expecting to see. And this is basically what that equation is drawing for us. You see that E term in the equation? That's the exponential decay. That's the damping, the brakes, doing their job over time. And that sine term? That's the oscillation, the wobble. Put them together, and you get this beautiful decaying sine wave.
A sketch on paper is a great start, but let's see if we're right. We're going to use a really powerful simulation software called PySpice to build this circuit in a virtual lab and check if its behavior actually matches our math.
And here we go, check this out. This simulation shows us the current for three different values of our resistor.
Just look closely at how changing that one single component completely changes the circuit's personality.
Now let's zero in on our case study. The 160 ohm resistor, the one in the middle, peaks at just about 0.7 amps. It's a perfect match for what our theory predicted. And you can see the trend, right? A smaller resistor gives you a higher, bouncier peak, while a bigger resistor really tames that oscillation. This is that tug-of-war we talked about, playing out right in front of us.
So you might be thinking, okay, this is pretty cool, but why are we so focused on this bouncy, underdamped behavior? I mean, in a lot of electronics, oscillation is a huge problem you try to get rid of. But in power electronics, well, it's a tool.
This quote from our source material really says it all. We often design these circuits to be underdamped. We do it on purpose. That oscillation, that bounce, it isn't a bug, it's a feature, and it's one we can use.
And here is the /1 reason why. By taking a DC voltage and switching it into an underdamped RLC circuit, we can generate a pulse of current that looks an awful lot like 1/2 of a perfect sine wave. And that is the fundamental building block for things like power inverters that turn DC power into the AC power we use every day.
So this is really the big takeaway. By carefully choosing our R, L, and C values, we're not just building a circuit, we're literally designing its personality. We can control the peak current, we can control the frequency, we can control everything. And that level of control is what makes all of modern power electronics, from your phone charger to electric cars to giant solar farms, possible. So I'll just leave you with this thought. Now that you know how to control this circuit's personality, what could you build with it?